Okay folks, last video of our module 8, we are going to construct molecular term symbols just for our simple diatomic molecules. This will be really similar to how we constructed atomic term symbols, of course, but now we're doing this for molecules. And we're only going to do this for very simple diatomic molecules. So here is our main term symbol. There are some similarities to the atomic term symbols. So for one, 2s plus 1, right? That is the multiplicity. So, that describes if we have a singlet state, a triplet state, and so forth. This is a capital lambda, and that describes our total orbital angular momentum quantum number. Total orbital angular momentum quantum number. And P, this is different than what we did with atoms. This is known as parity, and it is our symmetry term related to if it is Gerard or ungerard. Okay, so a couple ground rules. So first, let's talk about lambda, the main term. So lambda we get from adding up all of the individual lambda values. And those individual lambda values are based on if we have a sigma bond or a pi bond. So for example, when we have a sigma bond, little lambda equals 0. When we have a pi bond, little lambda is plus or minus 1, and it's arbitrary which one we choose as long as we are consistent. So one way that I like to be consistent is I always call pi x plus 1 and pi y minus 1. You can switch those if you want as long as you are consistent. And so finally now, when we add up all of those values, the absolute value of lambda is very analogous to what we did in atomic term symbols. If it's 0, we give it a sigma. That is analogous to S from atoms, right? If it's 1, we give it a capital pi, analogous to P. And if it's 2, we give it a capital delta, which was analogous to D. So as one example, if I look at something simple like H2, that has a molecular electron configuration of 1 sigma G2. So now the way that we would put that main term together is noting there's 2 electrons. Each electron is in a sigma orbital, so that would be 0 plus 0 to give me 0, which would correspond to a sigma term. So similarly, if I look at the electron configuration of nitrogen, I'll just go ahead and note that in the valence shell, it is 1 pi x u2, 1 pi y u2, and 2 sigma g2. So we have 6 electrons to consider there. And this is where we can see this arbitrary nature of whether we're going to do plus or minus. So I'm going to do plus 1 for x and minus 1 for y. So that would go plus 1, right, because I've got 2 in the pi x, minus 1 and minus 1, because I've got 2 in the pi y, and 0 and 0 for the 2 sigmas. Well, you might notice that all adds up to 0. So this would also get a sigma term. Okay. So let's keep going with that and talk about the multiplicity. So similarly to what we did before, we could either add up all of the individual S values, or we could just recognize when we have a pair, that is a singlet state. So that means, so let's actually back up. So when we have a pair, we note that S is equal to 0, and thus the value of 2 times 0 plus 1 is 1 for a singlet. When we have 2 unpaired things, we know we're going to get an S equal to 1, and 2 times 1 plus 1 is 3, right? So that means the same thing as it did before, our singlets and triplets, which will really be the only common thing we observe in simple molecules, right? Certainly if we talk about radicals, then a doublet state is possible, right, with one unpaired electron. So now we also have to consider the parity. Okay, so when we have a G times a G, it gives us a G. So that's kind of equivalent to saying like a positive times a positive gives us a positive. When I have a U times a U, that gives me a G. So that's the same thing as saying a negative times a negative gives me a positive. And when I have a U times a G, I get a U, or in other words, a negative times a positive gives me a negative. So if we go back to those examples of H2 and N2, right, we note that it was 1 sigma G2. We already established that it was a sigma state. It has to be a singlet, right, because we know that those are paired up. And both of those electrons are G, right? So G times G gives me G. Okay, lovely. So now what about our example of nitrogen? So once again, that was 1 pi x U2, 1 pi YU2, and 2 sigma G2. So we already established on the previous slide that that was a sigma state. So, and we might also just be able to look at it right away and recognize that has to also be a singlet. Everything is all paired up. So now what about our parity? Well, we're going to have, let's see here. So U is a negative. So I've got 2 negatives to give me a positive. I've got another situation with 2 negatives to give me a positive. And then I've got a situation over here to give me 2 positives to give me a positive. So I get positive symmetry terms all around. So I can put a G right there. Now finally, there's one last special term that we need for sigma states only. So sigma terms only. And that's going to be if our orbital changes sign when we cross the internuclear zone. So if we look at this sigma bond, and I want to be very clear, when we say sigma terms, I am referring to the capital sigma, not necessarily the sigma bond. As we shall see, we can make a sigma term from pi bonds. So if we look at this sigma bond and recall that it has this cylindrical symmetry about the z-axis, we don't have a change in sign for this particular sigma bond. So because of that positive, positive, we include a positive sign on this sigma term right here. That's going to change with our next example. And you'll see why it's important to note for sigma terms, not sigma bonds, but sigma terms only, we have to indicate this additional term symbol, the positive sign. And now what I also hope you kind of recognize, this singlet sigma G plus becomes a very common term symbol for most simple atoms or simple molecules. So, but of course, we can come up with an exception for that right away. And let's do that. That's oxygen, right? So let's go through and do that example. So we know from oxygen, we're going to fill out the 2s block, which will fill out the 1 sigma G and 1 sigma U, right? We had 2 electrons from each atomic orbital. And then we have 4 p electrons for each oxygen atomic orbital. So that means I need to bring 8 electrons down here in total. So we will go 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now let's build up a term symbol from that. So we first have to add up all of our pluses and minuses, and we'll start with the valence. And we really only need to worry about the valence. So remember, lambda is 0 for a sigma and plus or minus 1 for pi. So we'll have 0 plus 0 for these two. We'll have a positive 1 and positive 1, and a negative 1 and a negative 1. So positive 1, negative 1, negative 1. And then now, similarly, we'll have a plus 1 and a minus 1. So we will get 0. So we will get a sigma term for O2. And similarly, we did that for nitrogen already. Let's just do that to compare once again. So nitrogen has the following configuration. We know we'll fill out the 1 sigma G and 1 sigma U. And now we need to bring 6 electrons down here in total. That will go 1, 2, 3, 4, 5, 6. So hopefully you can see by now all of those will zero out to give us a sigma state. So, and then if we finish this off for nitrogen, recall we came up with 1 sigma G plus. So it might seem like, oh yeah, we should get the same thing for oxygen because Harman said this is the case for most simple molecules. It will not be a 1 sigma G plus. So let's go through it. So first of all, hopefully what you recognize, these two most outer electrons in O2 are making a triplet state, right? Those two outermost electrons and the non-bonding pi orbitals are not paired up, therefore they do make a triplet state. If we were to go through the same argument of the parity, right, we'd have G times G gives me G, U times U gives me G, U times U gives me G, and another G times G to give G. So we would still have sigma G, but now we need to indicate the parity of this situation. And so if we look at this here in the pi x state, our sign changes as we cross that internuclear zone. But compared to the pi y state, our sign does not change. So when we go through and do this symmetry operation, right, we're going to have positive, positive, so that's all good. We'll have a negative, negative, that's going to give me a positive. We'll have a positive, positive, that's going to give me another positive. But now look, because of this triplet state, I get a negative, positive, so I have a negative term right there for my O2. Thus, the molecular term symbol for O2 is different than that of N2. And O2 is a weird molecule. It is a triplet ground state. Okay, so one last term to consider, and that's with respect to spin orbit splitting. And this is typically only important in doublet states. So let's see, typical for doublets, because if you recall when we talked about atomic spectroscopy, we do get splitting from doublet states if the electron can be up or down. So here's a good example. This doesn't say no, so that's nitrogen monoxide. And so recall, the more electronegative element will be slightly lower than the more electropositive element. So when we put all of this together, we're going to end up with the following. So we'll have the lambda values, right? 0 plus 0 to make 0. Positive 1 and positive 1, negative 1 and negative 1, so that all zeroes out. But then finally, that one unpaired electron is going to give us a value of 1. So that's going to create a pi state, okay? So we can see there's one unpaired electron, right? Because this is a radical. So that means it's a doublet. So now noting this omega value, for us, it's going to be the absolute value of lambda plus s, where s is plus or minus 1/2. And so because lambda equals 1 there, we're going to get values that it can be 3/2 or 1/2, just like we saw with atoms. So we typically only note this value for doublets. Okay, so how do we apply all of this? Well, I lied. I did say there was one. That was the last term symbol. There technically is one final term symbol for molecules, and that is to indicate what state we are in. So X marks the ground state. So this is universally accepted. We use an X to indicate the ground state. And I'll point out here, this is our energy solutions for O2. So this is the O2 molecule. So you can see our lovely bonding configuration. And we determined that the configuration for O2 was triplet sigma G minus. There it is. I know that's really hard to read. And we put an X in front of that to indicate it's the ground state. So now A will be used for the first excited state, B will be used for the second excited state, followed by C, D, E, etc. And typically we use either a capital or a lowercase to indicate that the multiplicity has changed. So for example, if we look at the very next state up, it's a singlet, delta G, and now because the ground state was a triplet, it goes from being a capital letter to a lowercase a. You notice now the next excited state is a singlet sigma G plus, so we give that a lowercase b. But now, as we're going up here, we encounter our first triplet excited state. So that starts the lettering over, and we have capital A to indicate our first excited triplet state, and then capital B to indicate our next excited triplet state. So there is a little bit of wonkiness the way that's used. Sometimes it's not always used consistently, but generally when you see that letter change from an uppercase to a capital, it's another way to indicate the multiplicity is changing. So here's another good example. So this is BR2. I was just about to write B2R. So this is molecular bromine. And you can see that it has a singlet sigma G plus term symbol, a very common term symbol. And now, as you can see, X marks the ground state. But now this particular figure wasn't really consistent with that switching of letters. So there is a little bit of inconsistency there. So just be warned of that. But all the same, you can see here that it does follow A, B, C, but they didn't start the lettering over when they got to that first singlet state. So again, there is a little bit of inconsistency there, but universally X marks the ground state, and then you will generally see A as the first excited state, B as the second excited state, and so on. Okay, we're going to dissect these kind of diagrams in much more detail during our live lecture. Okay, folks, I'll see you later. This concludes Module 8.